the distinguished audience who are here to listen to my this lecture. I'll just keep it very brief. The idea is to just give you the major milestones of the research contributions that I have made in the area of solar photovoltaic technology. I actually work in renewable energy, basically, and power electronics. So power electronics is basically my main area, but we apply it to power quality and renewable energy conversion, which, as you know, is a very important topic today. So I have chosen solar PV technology and the contributions made in that. So very quickly, why people are talking about renewable energy is basically because of 2 or 3 reasons. One of them is that the fossil fuels, they are getting depleted very fast. So we all know that they will probably last for another 100, 200 years. The other is that everybody knows that when we burn fossil fuels, they actually release a lot of toxic gases in the atmosphere, and that actually causes a lot of problems to the health and so on. The third thing, of course, is a very important factor, which is the cost. So these fossil fuels are expensive, and they are actually getting expensive. And in the past, we have seen the complications that arise due to the economy of fossil fuels. So basically, because of all this, we can conclude that there is a need for a clean, abundant, and economical energy source, which can be, which won't cause any toxic gases to be released, won't affect the health adversely, and so on. Now, there are several options which mankind is considering. There are people who are working on this, and of course, the options that I have listed on the screen right now: the solar photovoltaics, the wind energy, the fuel cells, tidal energy, and this list is very long actually. So just listed some of them. They're all having their own advantages and disadvantages. But it appears that the solar photovoltaics currently they have an edge, and they are leading out in the complete list of contenders. Solar photovoltaics is leading. Now, solar photovoltaic is a very clean source. There is no noise as it operates. The maintenance requirement is not very rigorous. And the lifetime is about 20 to 25 years. And what exactly when we say solar PV it is nothing but a PN junction on which the solar radiation is falling. And the photons which are falling on it, they actually knock out the electrons, and they actually flow through the load, forming the electricity. So basically, a solar photovoltaic cell in the basic form unit, it actually gives DC electricity when the solar radiation falls on it. But obviously, with one cell, you get very low voltage and low current. So what we do is that we connect many of them in parallel and in series to get appreciable voltage and current capability. So now this becomes a more practical source which we can think of using to drive electrical loads. So a typical power electronic system that is used along with the solar photovoltaic source is what is shown on the left side. So you can see that there is a power converter, which here is taking a DC electricity at its input, which comes from the solar PV, and it gives the DC electricity to the load, which is connected on the right side. Now the problem comes because of the very non-linear characteristics of the solar PV source. So, I mean, you know that the power supply, typically, let's say what we use in the lab or even a battery, this will actually typically would have, if I could just draw here, annotate here a little bit. So I can say my voltage and current would be somewhere like this, it's more like linear. It might drop, but it will be linear. But if you see the characteristics of the solar PV, it's all the way like this. So it's a highly nonlinear characteristics. So basically what it means is that if you see your PV, this is how it is, the characteristics is looking like. So basically the idea is now, if you plot the power that is coming out from the PV source, as you operate your system, you can say that at every point here, I just multiply I and V. So basically whatever is the voltage here, and whatever is the current coming out here, I just take their product. When I do that, for such a characteristic that you see, you find that this red color characteristic comes, which gives you the power. So if you see this right side, I have written power, and on the lower side, on the x-axis, I have written voltage. So you see that your I, how it is varying with respect to voltage, and then power, how it is varying. So clearly, if you see this point here of this bell-shaped curve, you find that there is a unique point which is called the maximum power point of a source. And if you want to utilize your PV source to the maximum, you must operate at this point. Now, how would you do that? To do that, you must actually present such a load with this combination, such a load to the terminals of the PV source that it corresponds to this point. So this R1, R2, basically under two different conditions of radiation and temperature, maybe, we're just trying to say that these are the two, the load curves that you can draw, and you can see that wherever they are cutting the IV characteristic, that is the point where the maximum power point or the operation is taking place. Okay. So basically what I'm saying is that with the combination of this DC to DC converter and this load, you actually try to adjust in such a way that you present such a resistance to the solar PV that it gives out maximum power. So we can do this by varying the load curve. That means that would be actually meaning that somebody has to go and keep varying the load, which is not possible. So DC to DC converter, they have a control, which is in terms of the duty cycle of the power converter, which can be done, and you can actually show that actually that variation of the duty cycle of the power converter in conjunction with the load will present this variable resistance to PV. And then you can latch on to the point which corresponds to the maximum power. So this is one big challenge which we have basically tackled in our research. The other challenge is because of the very commonly occurring condition across solar PV, which is called the partial shading, or I've not written it here, but actually it is non-uniform illumination. So we have actually, you can see there are two pictures I have shown left and right. You can see that there are some three PV modules on the left side, and there are some on the right side, three of them. On the left side, you see that the diodes are missing. Now, what happens is that when you are not receiving insulation which is uniform for all these modules, and let's say that one of them is completely shaded or is highly shaded, which means that it is hardly getting any illumination. And you can see that these three modules are in series. So obviously, because of these shaded modules, the current in the string would drop. And it actually, unfortunately, will correspond to the least current. So if basically a module is completely shaded or doesn't receive any illumination, while the other modules might be receiving, there is no way the current can flow in the string and supply a load which might be connected here. So this might be the place where your load might be connected. Nothing will come out here. So one of the ways is that you connect what are called bypass diodes. So these bypass diodes, you can see that they are placed across each of the modules, and their job is just to allow basically the unshaded modules. Okay, so like for example, you see this one. This is not a shaded module. So if the current can flow through this module, it can flow. Let's say it cannot flow through module 2 and module 1 because they are shaded. They don't have any illumination. So then the current can take the path through these bypass diodes, these two, and it can flow through the load like this. So that is why these bypass diodes are almost now inbuilt in the PV source, the PV arrays, the PV panels that we buy. Okay. There are ones which are without bypass diodes also, but most of them are now available with bypass diodes. Now the problem is that when you have a bypass diode, the problem comes that you get very strange characteristic of the solar PV. It is no longer this kind of a characteristic that I have shown you. It actually becomes even more complicated. So you see that the IV characteristic, if you actually take, if you consider the two modules, let's say these ones in series, so the current that will flow through them will be the same, but the voltage that will appear at the output will be the sum of the voltages across module 1 and module 2. So when you do this, you are given the characteristics of the module 1 and module 2. When you add the voltages and also you see the current, which is common to both the modules, you find that you get very strange characteristics. So as you can see that there is a step here in the current voltage characteristics. And if you see the power voltage characteristic, this one, you see the power voltage characteristic, you can see that this particular feature, when you take the product of voltage and current at all the points, you find that it gives you this kind of a behavior. Now, if you compare this with this kind of a waveform, okay, and if you remember, I showed you this bell shape Okay, the curve, it has only one unique point. Now you have a characteristic which has two peaks. Okay, now only one of them is global peak though. The other is just a local peak, but it is there. So if my algorithm is designed only to handle uh, single peak systems, as is the case, as people thought in the beginning, and they actually devised all the algorithms based on that, you cannot track the maximum power point of the system which is having this characteristic. It probably will get trapped here. And mind you, I just given you a 2-module example. Actually, there would be hundreds of them in series. So this will be really very, very complicated. So this will have many uh, of these peaks, only one of them be local peak. So there is this work that we did on the two things. One is that how to model such systems. We need to understand these exact characteristics, how many peaks they have. Okay, where is the global peak, whether it is towards the left or towards the right, and so on. So one is the need for modeling, so that you can actually then interface your circuits with such a source and then study how and with what efficiency and what effectiveness the system would work. While the other is how to actually do a maximum power point tracking in such a situation. So these are just some other examples where I have actually included, as you can see, more number of modules. Now there are two strings which are in parallel and so on. So their characteristics I've just tried to show, they will be very complicated as well. And they go on becoming more and more complicated. So one of them is what is called the global maximum power point tracking. So it basically, you try to extract the global peak, not the local peaks. So you actually try to leave out the local peaks and work with and somehow try to reach the global peak. So there are several people who have done work on that, but they don't really guarantee that you will reach the maximum, the global maximum point. So there's one work that we have done, which has been highly cited, which actually is on the maximum power point tracking of such systems, which is, as I said, it's also called partially shaded conditions. Now, another way people are trying to overcome this problem is by, using dedicated converters along each module. So basically, you can see here, if I can just show you with this pointer here. So you have a DC to DC converter here. We have more modules here, and each of them have a DC to DC converter, and you have a DC to DC converter all the way till the end. And what it does is basically this DC converter, it tries to compensate for the current, whatever may be the current through the string corresponding to the maximum or the most illuminated PV module. Basically, the converter tries to make sure that the current flows there in the string, it corresponds to that maximum illuminated module. So this is actually called the distributed maximum power point tracking, where you are using power converters, and there are some certain variations of this as well. So we have worked on quite a few of these, and one such paper that I can just list here for your references, the one which we published in 2013 in IEEE Transactions and Products. Okay, so I just told you that the partial shading characteristics are very complex. So we have actually worked on the how to really model your PV source, okay, with n number of modules and see what their characteristics would look like, how to model them using a simple and easily available software that everybody has, MATLAB. There are other specialized softwares which people have been using, but they are not really the ones which you can interface with your circuits. Okay, so this MATLAB based model that we presented was a simple one where we just introduced some terminology and nomenclature, and we just try to model this in MATLAB. So how many modules in series, how many assemblies we can divide them into, how many groups, how many subgroups, and so on. And then we were able to basically feed this topology into a simple MATLAB program, simply as an array. We just put this information, and then it gives us, it gives us the characteristics. So these are some of the screenshots that I have put here. When the software runs, it actually tries to give you the characteristics of these solar PV source under, as you can see here, under partial shading. So as you can see here, these characteristics here, C1, C2, C3, you can see that one or more of these modules is shaded. So you can see that there is a hump coming in here. There is a step that appears here, and there could be cases where you have more number, many, several numbers of these curves or these humps might be there. Okay, so that is our work that I wanted to highlight in the direction of maximum power point tracking and maximum power point tracking under non-uniform illumination or partial shading condition. The other area in which we have focused quite a bit is are the grid connected systems, which you actually usually see in the rooftop. Many of these buildings now currently have solar PV systems which are installed. So there is a solar PV. It's usually there are two-stage systems where the first stage is used for maximum power point tracking, and the second one is actually used, as I told you, if you remember, that a solar PV source is a DC source. Okay, so it actually the DC to DC converter that we have put, it actually gives you DC. Now most of our loads are AC, so that is why there is a need to convert this into AC. Now grid connected systems have become very popular because there is no need for batteries. If these systems are not connected to the grid, then the solar PV output power that is coming out, that you must, if suppose you don't have a load which needs it, you must store it into battery. So you need battery also for such systems. But for grid connected systems, the battery is either eliminated or minimized. So these two-stage systems, now because there are two stages which are there, and a typical two-stage system is here, where you can see that the first stage is actually maximum power point tracking stage, a DC to DC type of converter. And there is a second stage, which is here, which is nothing but a DC to AC converter. And with the control, you can see proper control. I can do maximum power point tracking here. I can get the maximum power available. And then by doing a control here of this inverter, I can try to feed power into the grid. So usually whatever available power is there for PV, usually, if you have local loads, it actually feeds that, and the surplus power is actually fed into the grid. And you actually have these meters which are put here. And these meters are bidirectional meters. They can actually then tell you that you are whether you are feeding power into the grid or you are drawing power from the grid. So this is a bidirectional metering which has become important now, ever since these systems, grid connected systems, have come into effect, or they have started functioning. So they actually count that how much money the electricity or utility has to pay you, because you are supplying electricity to the grid from your solar PV, and vice versa. Now the thing is, you saw there are so many stages, and I told you that typically if you see the efficiency of such a system, if the efficiency of the first system is N1 and efficiency of the second system, this system is neta 2, neta 1 and neta 2, then the net efficiency will be neta is equal to neta 1 into neta 2. Now this actually causes a reduction in the efficiency. The question is, can we have this boosting, and you have that, and then you also have the DC to AC conversion. So can you do all these things within one stage? So we actually have worked quite a bit in the last few years on this, and this is just a depiction of what I was just trying to say. This is one such system which I cannot explain in detail right now, because it's a power electronic system which implements a two-stage system into one-stage system. So it's actually connecting to the grid on the right side, what is actually coming out from the solar PV source. So again, we have a highly cited paper on this, and many other papers which we have written on a large number of the work that we've done, several converters that we have actually generated. So you can see here the typical waveforms of such a system. You can see there are two waveforms here. One of them is this lower magnitude voltage waveform, which is for the current that is going into the grid, and this big one that you see, that is the voltage of the grid. And this is just the harmonic analysis of the current that goes, because we are bound by certain standards and we can exceed the total harmonic distortion in the current. This is another work which is a universal work converter for the grid connected system, but it's just an example of that. And again, I cannot explain the full working of this, but this more or less explains one such another very important example of grid connected system. So there are some issues now. As we know that the country is trying, in fact, the whole world is trying to feed a lot of power into the grid. So what will happen if such a large PV source is feeding power into the grid? So obviously there is a need to study what will happen to the stability of the grid when such a large source, which is several gigawatts, is feeding. So, so there are many researchers who are actually looking at this when you will be feeding such a large power. So with this, I'll conclude my talk, and I'll be happy to take questions.
So thank you very much, Professor Agarwal, for giving us a very nice overview of your work. There is one question from S. Ananthakrishnan. What is the maximum efficiency achieved after taking care of all aspects during the hours 10 a.m. to 4 p.m.?
There are two things. Whether we are talking about the system efficiency or we are talking about the efficiency from the point you are getting the solar radiation, how much solar radiation we are getting, and how much we are converting into the to electricity. So as far as the efficiency of the radiation to electricity, that conversion is concerned, that remains about 17 to 18% at maximum. That is not beyond that. And that depends on the solar PV technology. But the power electronic systems that we are using after that to convert the power into the form, suitable form, now they are actually having a very high efficiency. They can actually give you efficiencies of almost 96% to 97% these days.
Thank you very much, Professor.